Alrighty, we are going to do a video on Atwood's machine. Atwood's machine is a system of masses that will accelerate, and it's a teaching tool. Can't think of a practical use for this, but it's a good thinking tool. So Atwood's machine is basically a pulley that is suspended from the ceiling. And let's draw the pulley, and then let's draw some sort of support mechanism for the pulley. And you put a rope over the pulley, and you hang one mass on one side, and I'll call this cleverly mass 1, and on the other side you have another mass, and I'll call this mass 2. Now mass 1 might be more than mass 2, and they might be equal, and mass 2 might be more than mass 1. And we'll have to deal with it. I think we understand that if mass 1 is heavier, this thing will accelerate with mass 1 going down and mass 2 going up. If mass 2 is heavier, it'll go down and mass 1 will go up. And if they're both exactly the same mass, then it'll hold still, or at least have no acceleration. So, a couple different ways to solve this, and let's do the more classic way, which is to draw a free body diagram for each of the masses. So for mass number 1, there is a weight that mass number 1 brings to the party, and that's m1 times g. But pulling upwards is a tension. Yes, the tension in the cable is pulling upwards, and that tension is the same everywhere throughout the cable, but we're not sure that it's the same as m1g. Remember, this system could be accelerating, in which case these forces would not be equal. And then m2, is going to have its own weight, m2 times g, and tension pulling up the other way. And so you can see the role of the pulley is just to change the direction of the rope so it can pull upwards on both of these masses. Now, from here, well, before we really get started, there's an important step, and that is to deal with the coordinate system. You see, if mass 1 is heavier and goes downwards, I would like to call that positive. But that means that positive for mass 2 is going to be upwards. And you can summarize this by putting just a little curved line up here around the pulley showing which direction of pulley rotation would correspond to positive motion. So I'm going to choose this direction to be the positive direction. And now we can write F net equals m times a for this guy, and we can write F net equals m times a for this guy. And F net for this guy is m1g minus t, and that's going to equal m1 times a. Over here, t is the positive force, t minus m2g equals m2a. If you don't do this thing where upwards is positive for one and downwards is for the other, you wind up getting the acceleration has two different meanings in these two equations. Here, the acceleration means the same thing, the acceleration of the system. So we have two equations and two unknowns, t and a are unknown. So let's go ahead and take this second equation and let's work it around. So t equals, and we'll bring this negative term to the other side, m2a plus m2g. And let's substitute that in over here for t. So we're going to have m1g minus m2a minus m2g equals m1a. So I solved this one, substituted it in over here, and now I've got this thing. And we can collect terms, and we can get the a terms onto one side and the g terms onto the other. So we're going to have m1g minus m2g on this side. And on this side, we're going to have m1a plus m2a. Collecting and factoring out things, we're going to have m1 minus m2 quantity times g, and that's going to equal m1 plus m2 quantity times a. A turns out to be, dig this, m1 minus m2 times g all over m1 plus m2. And this is a general result. We haven't put any numbers in, so this is always true for an Atwood's machine situation. And take a look at it. It's really kind of elegant. It has all the things in it that you would expect. For example, if m1 is larger than m2, this term is positive on the top, and the acceleration will be a positive number. If m2, however, is bigger than m1, this term on the top will be negative, and this system will move with an acceleration in the negative direction. And if these two are equal, the term on top is 0, and there'll be 0 acceleration. That's really pretty cool. The other cool factor is on the bottom here is we have an inertial term. All right, it's m1 plus m2. In other words, what's slowing the whole system down, slowing it down because it's on the bottom of the fraction, is the combined mass, the total inertia of moving this whole thing back and forth. So this is really kind of elegant. Also, this kind of looks like A equals F over M, where F here is some sort of, force differential, and down here is the total mass of the system. And that kind of leads us to another trick, a way you can solve this problem, and that is the system trick. And we've talked about this briefly, but the system trick for the Atwood machine would mean imagining that we took this apparatus off of the pulley and just kind of laid it out, and then we imagined when it was on the pulley what was pulling it to the right, which would be like the negative direction, and that would be the weight of M2. And what was pulling it to the left? Well, that would be the weight of M1. And let's furthermore remind ourselves of two things. One is that this direction is the positive direction. And let's remind ourselves that the total mass of this object is M1 plus M2. So now we can write Newton's second law for this compound object. The net force is m1g minus m2g, this force minus that force. The total mass of the object is m1 plus m2 times a. And in one step of algebra, we're already down to here, well, here at least. So we can collect terms, m1 minus m2 times g, divide by that thing there, m1 plus m2, and we get our acceleration immediately. What we've gained in ideation, in thinking, that work of thinking has gotten rid of a lot of this algebra, just beating things against each other. Now, the problem with the system trick is that if somebody asks us for the tension is actually an internal force to our system. So we are forced, excuse my pun there, to draw a free body diagram for one of the two masses. I'll do M1G and T in order and analyze just this situation in order to figure out what T is. And so this one, with the downwards being positive, we would say M1G minus T equals M1A. Monkeying this around, we would have M1 times the quantity G minus A equals T. And then we would put this whole thing in for A. And it's kind of ugly, but let's just get through it. M1 times G minus M1 minus M2 times G over M1 plus M2, and all of that equals T. There you can factor out the G, so we have M1G out here. Oh yeah, we never did substitute back in and find the tension on this side. Isn't that interesting? The way to handle this thing in parentheses is to realize that it is M1 plus M2 over M1 plus M2 minus M1 minus M2 over M1 plus M2. In other words, I wrote the 1 that was here as M1 plus M2. Common denominator is what I did here. Okay. Then you would combine this by taking M1 minus M1, 0, and then M2 minus a minus a plus, so M2, that's 2M2. So we wind up with 2 M1 M2 G over M1 plus M2 equaling the tension. So that's the result. And it's the same result we would have gotten over here had I finished this problem. I did not finish this problem. All right, so this is Atwood's machine. It's a really interesting thing using the system trick or using the system of two equations, two unknowns, two free body diagrams, two turntables, and a microphone. That's it for this one.